Well, good afternoon, everyone. My name is Whitney Stoll. I'm the DC Post president. Thank you all for being here today, and welcome to our second First Friday webinar series. And today is Power on the Move: The Promise of Mobile Nuclear Technology, with our presenter Chris Pearson, the CEO of Mobile Nuclear Energy. Joined by me is Samantha Long and Bree Beal, who are behind the scenes moderating our webinar today, and will also be monitoring the chat. So we have nearly 150 registered participants from all over the world, so ready to learn about today's First Friday webinar. So please join me in welcoming our guest presenter. So Chris is going to share with us some of the advancements in the technology that are driving the resurgence of in nuclear power, particularly with the introduction of small modular reactors and nuclear reactors, and in particular what we all need to know about the technology, regulations, and challenges in public perception as we look into the future of the energy industry. But first, I'd like to start to welcoming you all to our First Friday webinar series, which is provided to you through SME's commitment to offering the AEC community effective training, development, and networking programs. The DC Post is helping sustain the future of the profession with these monthly education-focused sessions, aligned with the SME's strategic goals to drive partnerships, deliver solutions, and develop people. So thank you all for joining us here today. So please feel free to use the chat, introduce yourself, share your LinkedIn profile and contact information, also where you're calling in from as well, to everyone throughout the presentation. Ask questions so we can address them during the Q&A portion at the end. For those who are using the WebEx desktop application, you have the option to save the chat by going up the file, down to save, and then save chat. We are recording this webinar, and the video on our YouTube channel will be available on our YouTube channel later on this month. A copy of the slides, your PDH certificate, and an opt-in list of the attendees will be emailed to you as soon as the webinar ends. So look out for document delivery at the subject line with your download following the webinar. So thank you again for joining us. We're really excited to provide you an hour of education and virtual networking, no matter where you're calling in from. We would like to take a moment to thank our DC Post First Friday sponsors, Fox Rothschild, KCCT, and Parsons Corporation. We truly appreciate your support, and we are grateful for your generosity by making this webinar series possible. If you're not already a DC Post sponsor and would like to support our post with annual sponsorship, we would love to add your name to this slide for future programs and events this year. Annual Platinum sponsors and First Friday sponsors help support this webinar event with free registration for SAME members and full-time students. So please feel free to visit our website for more information about the sponsorship levels and how you can give back to the SAME community through your DC Post sponsorship. So now it's time for the main program. And please note this program will provide one professional development hour from the DC Post. So I'm not going to read the learning objectives on the slide since most of you saw them. The same objectives when you registered. Instead, I'm going to introduce to you our featured speaker in just a moment. And when I do the introductions, if you haven't already done so, please feel free to use the chat, introduce yourself, and share your contact information. This is your webinar series for help you learn on this special topic. While using the chat, share any comments or ask questions to our presenters. If there's a particular slide you want to talk about, share that detail in your chat question, and we'll be sure to answer all the questions in the chat at the end of the program. And don't forget to save the chat before you exit the webinar. And now please allow me to introduce our presenter, Chris Pearson. And Chris is the CEO of Mobile Nuclear Energy, bringing us over 35 years of leadership experience in the defense aerospace sector. Chris is a retired U.S. Air Force colonel. He has held leadership roles at companies like Huntington Ingalls Industry and General Atomics. He also founded Apogee Professional Solutions, which is a consulting firm focused on empowering defense clients. Chris is a decorated command pilot and electronic warfare officer with over 3,000 flight hours and holds advanced degrees from Boston University, the Air Force Institute of Technology, and the Air War College. So welcome, Chris. Now I'm going to turn the program over to you.
Great, thank you, Whitney. And it's welcome, very warm welcome. I appreciate that. It's great to join you in the same community here on the afternoon webinar. It's a real opportunity for me to share my excitement about this technology, where I think nuclear energy is going with the new introduction of small modular reactors and microreactors in particular. I'm going to share my screen here and we'll get right into the presentation because there's a lot of information and I know we're limited on time. I think this community in particular is really aware of the energy challenge that we're facing as a nation. I really believe that energy is key to national power, both abroad and at home. Increasing demand is just rising off the charts exponentially. From the military perspective, abundant, really available energy is the backbone of our operations. Modernization, like electrification of vehicles, the introduction of high energy weapon systems like rail guns and lasers, high powered microwave, are just driving energy requirements even more. A statistic I like to talk about, something I learned early on when I got into this business, was that 90% of the logistics for for fuel and water in Iraq and Afghanistan over the past 20 years. So our expeditionary operations overseas, 90% of the movement on those supply lines was fuel to power generators, fuel to power aircraft, and then the water generation at the forward operating bases. The casualties incurred were a lot of IEDs, roadside bombs, and ambushes. Over 50% of the losses were actually on those supply lines. So if we can mitigate that vulnerability, we're going to directly save lives with power delivered to the front. Domestically, we've had a horrible last year with the hurricanes, and this year is off to another interesting start with the fires out in California. When the infrastructure is down, critical infrastructure, bringing power to the point of need, whether it's a modular power source itself like the reactor, or all those ancillary capabilities that can produce water, purify water, provide heating and chilling for facilities, really can restore that confidence in the civil population, prevent the unrest, and more rapidly recover from natural disasters. Not just in the States, but also islands like Puerto Rico or Haiti. Look at Ukraine or Israel today. The infrastructure is just obliterated. And if you can bring power to the point of need, you can rapidly restore that and recover quickly. So I really feel like I'm preaching to the choir here. Overall, the agenda, we all know what the challenge is. I'm going to talk briefly about the evolution of nuclear technology and where we are today. I'll talk about the case study. It's not really a marketing pitch for our particular reactor, but my company is developing the MN1 mobile power module. It's a 20-foot shipping container with a combined reactor and power turbine generator in a single package. We'll get into some details of that. The applications for that kind of a capability, challenges and risks that we're facing, and then how this community in particular can help advance these efforts. You notice in the bullet there, I say purpose is really to introduce mobile nuclear technology as a transformational energy solution. And I say again, because if we go back 60 years or more, we see that the Army had a mobile reactor with the ML1 mobile power system. And the first high temperature gas reactor was a Peach Bottom reactor in Pennsylvania, designed by General Atomics, actually, my previous employer. So these are not really new technologies. What has advanced, what's really changed the industry, to jump to that slide, out of order there. What's really changed, I think, is the technology, the generation of the reactors themselves have gone to what's called a first to fourth generation. The fuel has become not an open fuel cycle where the waste is just packaged up and stored somewhere, but the accident tolerant fuels, the way you can reprocess and recycle these, and then the higher enriched, the high assay, low enriched uranium fuel really increases the energy density and allows you to have some of these smaller reactors. The demand we talked about, it really is increasing exponentially. It's insatiable, it seems. You see the private sector investing, if you read the news with Google and Amazon, Microsoft, all investing big in these data centers, and they see nuclear as the solution to keep those powered and operating. Internationally, China, Russia are really starting to catch up, and they've embraced nuclear as a solution. We want to be a world leader in this technology, so there's a risk of us falling behind as other nations move forward. Some of our allies, like France, they already provide 70% of their national power through nuclear power. So the U.S. is really kind of fallen behind in that regard, and a lot of that was because of the perceptions of risk and some real world accidents, things like Chernobyl, 3 Mile Island, Fukushima in Japan. But it's interesting that not a single life has been lost in the U.S. due to a nuclear power plant malfunction. So, there's the real risk and the perceived risk. But I think the trend is trending favorably now. The public is starting to realize and appreciate the value of nuclear power that's added by the green initiatives, decarbonization, because nuclear really is the only baseload power that is a zero emission potential. Wind and solar, those are great, but they require a lot of real estate, big wind towers, and those only work where the wind is blowing and the sun is shining. But with nuclear, it really is that reliable um, power source. I'll go back and just briefly describe the technology. I don't want to insult anybody's intelligence, just as kind of a nuclear reactor 101. I think the reactor itself is really just a heat source. It's a heat source that has a long life, that's durable, and it burns consistently in any kind of environment. When you generate that heat, you need to transfer it into put it to useful work. So there's like a heat exchanger or some kind of way to get the heat out of the reactor. And then once the heat is out of the reactor, you can use it to do a lot of different things. You can turn steam generators, supercritical CO2 generators. You can use the heat directly for things like plasma treatment of wastewater to really break down any hazardous chemicals. The process heat can be used for industrial applications, steel production, whatever it might be. And then there's the recuperator side as well. That's just another way to capture more of that energy that's coming out of the reactor. For a typical gas-cooled reactor, there are many different variants of reactors, but the gas-cooled one has the pressure vessel, which contains the fuel cells and the moderator. The density of the uranium fuel, when it's packed in tightly enough, it reaches a point called criticality, where there's a sustained fission reaction inside the reactor, and you moderate that or you control that reaction with the control rods. So as you drop those black control rods down into the core, it actually slows the reaction down and will completely shut it down to stop the reactor. That's the source of the heat. You blow some kind of a coolant through there. In our case, we use a helium gas. Other reactors use nitrogen gas. The water cooled obviously use water. And then there's even some variants that use liquid metals or molten salts to draw that heat out of the reactor. And we'll talk about that briefly about what the different capabilities are and pros and cons of each type. The reactor itself is contained in some kind of a shielding or containment vessel. That's preventing the gamma rays and neutrons from harming the environment. That's a really critical consideration. The neutrons that escape can actually go out and what they call activate surrounding materials. So the reactor can cause even the ground or the water flowing through the reactor to become radioactive itself. And the shielding prevents that from going outside the boundaries of the reactor. The heat exchanger, many different types. One that I'm using in our reactor is a helium to supercritical CO2. So you have a primary loop that circles through the reactor, and then to isolate any contaminants and get it into the work side of the process, you have a secondary loop, typically water or another gas or something else to draw that heat into the actual generator or place where it's going to do the work. Go to the next slide here. Talk a little bit about the technology and what's changed. Generation 1 and 2, those were kind of the prototype developmental reactors after World War II that led into all the way up through the 1990s. The safety system were active. They had to actively engage to shut down the reactors or scram the reactors. The fuel was open cycle, which means the waste was not reprocessed, and it was just packaged up and stored in a waste containment area somewhere. You can kind of see the different features of these different generations of reactors. Moving into the 1990s to the present day, that's kind of where we are with the generation 3 and 3 plus. There are a lot of improvements, a lot of good safety features have been added. But the advanced technology that's in development now, what they call the generation 4, is really a step change in reactor capabilities. It's a fully passive safety system. So if you lose your coolant, let's say that cooling gas escapes in the reactor, just the ambient air itself can cool it down. There's no risk of a meltdown there. The fuel has what's called a negative coefficient of reactivity. So if the reactor reaches a certain temperature, the heat itself actually slows down the reaction. So it's not going to have a core meltdown. We talked about the different types of coolants, the gas, the salt and liquid metal, and then the sizes of the reactors. I highlighted their mobile because using gas and the small microreactors, what's really key to making a reactor able to be mobile. The gas, because it doesn't have a lot of latent heat, it can heat up and cool down quickly. So when we shut down a reactor, it can be ready for transport in a short time, where something like a salt reactor or liquid metal would retain that heat for quite a while and may need many hours or days to fully cool down before they could transport it. Proliferation risk, the fuel inside of a Generation 4 reactor, the HALEU fuels, they really can't be weaponized into a nuclear weapon. They'd have to be broken down and respun in centrifuges and basically refabricated. So the risk of proliferation is pretty low. We'll just go right on to the next slide of the fuels here. A couple different variants. TRISO is one that's become very popular now in the industry. This is the fuel kernel encapsulated inside multiple layers of carbon and ceramic. What happens when there's a fission reaction is the uranium actually splits into other elements. Those byproducts are called actinides, and the actinides themselves can be toxic. And what you want to do is contain those inside of a vessel so that they don't escape into the atmosphere or cause any environmental problems. And really, with this cladding, the particles themselves become their own mini containment system. So any actinides or gases that are released stay inside that little poppy seed size pebble. Same thing with the silicon cladding. General Atomics has a cladding called SIGA. That's a silicon carbide cladding that's actually like a woven weave that wraps around the fuel pellets, and those are all, again, sealed and become their own containment system. And a great feature of the new fuels is that the cladding and the containment, because the silicon has about a 2,500 degree melting temperature, which is it's over 1,500 degrees hotter than the reactor core itself. Our high temperature gas reactor that we're developing will have a maximum core temperature of about 900 degrees. The operating temperature is more in the range of about 650 or so. But that margin of safety there with the melting point is going to really prevent any kind of a meltdown again. Industry landscape, there's a lot of entrance into this space. The opportunity is really compelling. Again, it's the energy demand. I think the regulatory environment's becoming more favorable and positive. So you have about 70 entrants into the small modular reactor space. Everything from the transportable microreactors down at the lower left, all the way up to the larger reactors that are really a fixed facility. They're considered modular because they can be assembled in a factory or a fabrication facility, and then moved to the site and integrate the modules at the site to establish the reactor function. Of those 70 companies, less than 10 of them are really developing a true microreactor, us being one of them. And some of those are promoted as being transportable or relocatable, rather than something that's really truly mobile on an hour by hour basis, or possibly even provide power en route. Differences being the type of reactor itself, whether it's molten salt or metal, the amount of shielding required in the site preparation. So those are really the things that distinguish kind of a transportable reactor versus something that's truly mobile. And into our particular reactor design, it's a technology that kind of grew out of the Army Futures and Concept Center at Fort Eustis. This is back in 2018. The Army Futures and Concept Center had discussions with NASA Langley down in Virginia, and it was really a augmented or replacement capability for some of the Army prime power units. How do you really deliver power to the areas near the front, not necessarily on the front lines themselves, but close enough where it could provide energy to the soldiers in expeditionary operations, as well as restoring that domestic infrastructure that we talked about. So that was 2018. It just so happened that the Deputy Commander of Army Futures Command, General Richardson, was good friends with General Caslin. He was a retired general that was then the president of the University of South Carolina. So they took that concept to the university and initiated a research program. That was completed after a few years, and in 2022, the co-founders of our company formed a company to commercialize that technology. Fast forward to where we are today, launching the program. I just joined the company in June of last year. So it's really about commercializing this design that was created basically for the Army, but has all kinds of dual use applications across the military, national security sector, as well as the civilian sector. The reactor itself mitigates need for fuel and water, like we talked about. And it's really a new paradigm for delivering energy in a truly versatile and forward-placed capability. Features of the reactor, and again, this is our particular variant, but this would be typical of a lot of different microreactors that may be in development. We're producing about 1 megawatt of thermal energy, but a little better than close to 40% efficiency will give us 350 kilowatts of electric power based on that turbine generator. We're fully shielded, no necessary site preparation or standoff distance, and then no post-movement cleanup. Because it's the gas reactor, full operating capacity within 2 hours is our goal, and shut down in less than 4 just with ambient cooling. Basically, the reactor core itself is like 100 or 1,000 100-watt light bulbs that just need to cool off with the convection cooling of the air. And then I think another consideration is the systems of systems approach. We're not just building a reactor core, it's really a suite of capabilities, all that'll seamlessly integrate with the power module to do things like generate water from the atmosphere, provide that heating and cooling, hydrogen electrolysis to produce hydrogen fuel or hydrocarbon fuel, and then those EV charging stations at forward locations. All those, the vendors we're talking to about that, we're going to constrain them to that 20-foot shipping container size or smaller, and everything will be transportable and mobile. The nature of the reactor itself, it has much fewer moving parts than something like a diesel generator, so it's pretty low maintenance. We're designing to be safe and resilient to damage. We can discuss that more later. And then, of course, transportable. The definition of mobility is that it's going to be able to move by land, sea, or air. And we're really targeting that CH-53 sling load capability, not for high density altitudes necessarily, but if we can stay under that 16 tons, we'll be able to be actually transported by a helicopter in those exceptional cases. But a C-130 is definitely doable with the size and capabilities we're talking about. Then power on the move, this is really mounting it on something like a ship or some kind of a platform where the reactor could actually operate while it's in transit. The refueling interval is 10 years for our reactor design. And this is a little bit of an eye chart, but it really gives you an idea of how the MN1 microreactor would compare to a diesel generator prime power unit, because they're really kind of in the same class of capabilities. Obviously, the fuel of a reactor can go 10 years without refueling, whereas diesel generator is going to need a constant, not only fuel supply to feed the reactor, but all the logistics that goes with that, the transport, the personnel, the fuel storage on site. It really requires quite an infrastructure and a lot of expense to enable that capability. Operational efficiency, nuclear reactor is going to operate the same no matter where it is, up at high altitude or low, underwater, above ground. In any different environment. That's not true for diesel generators, high density altitudes, or at partial loads, they lose some efficiency. We talked about the logistics, and I think it's all those secondary and third order effects that really start to show the benefits of bringing this kind of power to the front. I've spent plenty of time deployed forward operating bases throughout my career, and always sucking the fumes from diesel generators so we can eliminate those emissions and go to a zero greenhouse capability with nuclear reactors. The resilience, I mentioned the fewer moving parts, so it's a lower maintenance, whereas the generators typically require an overhaul every 200 hours or so, depending on which generator it is. Safety and risk, the passive safety features we mentioned, the handling nuclear materials, that is definitely a regulatory concern, and making sure that we get that right as we move forward. That's why we're working closely with the regulatory agencies and everybody that's going to qualify and certify that capability. Diesel generators, again, not immediate risks or perception of risks, but there are vulnerabilities in that system as well. Something with the reactors, there is a cost. The nuclear fuel itself is pretty expensive, and unlike diesel fuel that's kind of pay as you go, the reactor fuel is a capital expense, a CapEx expense upfront. Usually pay for the fuel when the reactor is built, and then you amortize it over time. Whereas generators or other fuels would be an operating expense, would be paid as throughout the years of operation. But over the lifetime of the reactor, it really does make sense. You can see that chart there. The diesels, when you consider all the logistics, supply and support required, and how much fuel it would require to run for 10 years, you're looking at more than $2, almost $3 a kilowatt hour of cost there. Same for the natural gas generators, a little bit cheaper, but still pretty expensive. And then the amortized cost for our reactor, we're estimating is going to come in between 40 and 45 cents a kilowatt hour for a 10-year service life. And then after refueling, it could operate for another 10 years. So the reactor life itself is about 20 years, but with a midpoint refueling interval at the 10-year point. Just really the advantages. The reactor is going to be ideal for those long-term deployments. Just because it's mobile doesn't mean it needs to move around all the time. It could sit at a forward site for a long time. Remote off-grid sites, it's really that ideal for picking up and putting a C-130 or C-17, getting it to the area quickly, and then sitting there for a long term. Diesel might be a better option for something that's more short term, and you know that their fuel will be available. So we talked about the safety. I'll mention the helium coolant. That's an inert gas. It's not like hydrogen where it's going to burn. Helium doesn't react. It also does not become radioactive. So as it transits through the core of the reactor, it's not going to pick up any radiation. The fuel we talked about being clad and accident tolerant, the melting point. And then the fail-safe shutdown, those control rods, we're using control drums as well. All those are spring-loaded to a shutdown configuration. So for the reactor to operate, you actually need electromagnets to hold those rods out, and you need the electromagnets to hold the drums into an operating configuration. If you lose power or there's any kind of malfunction, those are spring-loaded to go into a shutdown. Same thing with the the helium loop. If you lose your coolant, the reactor go into a shutdown configuration. Again, it's a systems engineering approach. It's systems of systems. It's not just the reactor, it's the containment module and all those other modules that integrate with it. So we have to be able to withstand reasonable shock and vibration for a lifetime of use in the field. And then the vessel itself is going to be electromagnetic pulse hardened, as well as cyber vulnerabilities. We'll do a cyber risk management framework to make sure that the controls and any kind of attack vector into the unit is protected. Just a note about AI is going to have a place in this solution, or be part of the solution, because the AI is going to be able to monitor and could even remotely operate these, or there could be some autonomy to allow the reactor to self-regulate. It's really going to reduce some manpower requirements in those forward areas. We talked about some of these add-on capabilities. Think of the reactor as the core power module at the center. That's providing your electricity and process heat to enable all these other capabilities. Distributed microgrids, this is basically plugging into a grid in a forward area to power facilities. It could power your lodging area. It could power command post. It could power anything that you think of as electrical communication systems. Off-grid EV charging as we go to hybrid electric vehicles or full electric vehicles, things like the new Bradley fighting vehicle that'll be a hybrid. This is going to be an ideal forward capability to recharge those. Directed energy weapon systems, these are the lasers and rail guns that I mentioned before. Think of the Navy wanting to upgrade their legacy fleet of destroyers and equip those with counter UAS directed energy. Well, the extensive modifications to bring that power to the weapon system could keep the ship in dry dock for quite a while and be pretty expensive. But with our 20-foot shipping container, you could just place that next to the weapon system. It would just become like a single unit you could add on to the ship without doing extensive modifications. I mentioned the wastewater treatment. We can do plasma treatment. We can help with filtration systems, powering those. You get atmospheric water generation to give you that potable water. The hydrogen fuels, edge data centers, as we look at like the Titan targeting node or the AI fusion centers, Intel fusion centers, those are going to need power at the edge, and this is the perfect power source to do that. And again, combined heat and power. This is primarily for facilities. Think of a hospital that might need chilling, or food storage, something like that. You can actually do atmospheric absorptive cooling to provide air conditioning for those kinds of facilities too. We've got several vendors we've actually entered already with teaming agreements, and we're in discussions with many others as far as providing these capabilities. So I think this is going to be a great expeditionary solution for a lot of both military and civilian applications. A little bit of the target markets. Obviously, national security sectors is a big one. The National Guard bases put a few of these reactors strategically located throughout the U.S., and they'll be responsive for earthquakes or hurricanes, any kind of natural disaster. Would allow the rapid restoration of critical infrastructure. Operational energy for overseas, you look at the forward operating bases I mentioned in Iraq and Afghanistan, but if we ever have a conflict in the Pacific, we're going to do some island hopping. The Marines have their expeditionary advanced base operations concept, and the Air Force has the agile combat employment to enable those. Bringing your source of energy with you without the need for refueling is going to be a great operational capability and really add to the commander's flexibility. We've talked about I mentioned the power augmentation for legacy ships as they get modernized, but we could also be the propulsion and power for long endurance UUVs or USVs. Thinking about something that's doing a monitoring of undersea cables, or augmenting picket lines. Any kind of an underwater operation, rather than being underwater for weeks or days at a time. You could literally stay under for years and really automate that process. Underwater charging station for other electric UUVs, joint logistics over the shore. Think of a D-Day type invasion, or where you're bringing a lot of the logistics into a unprepared port. That's where you want to bring your power with you to power all the cranes and get the logistics and lodgement area squared away without a big diesel generator requirement. Again, naval facilities, critical infrastructure, and then some of the critical installations. Think of the COOP COG, continuity of government, continuity of operations sites like Site R or Mount Weather, providing enduring power so that they can stay in a button down configuration pretty much indefinitely, or until a crisis passes, or just for your training exercises. Same for the critical national command authorities with Stratcom and the nuclear infrastructure. Up in Alaska or Canada, the old DEW line sites, remote radar sites, and then maybe some embassies in the hotspots around the world. You think of some places in the Middle East or Africa where you'd want to have an enduring fuel supply for a U.S. embassy in case there's a crisis. On the civil side, the disaster relief is a pretty obvious application. We've also talked to National Science Foundation about things like McMurdo Station in Antarctica and some of the remote science sites. Not a huge market, but still a very critical capability. And then even state and local governments, you look at port facilities to keep those cranes operating to unload or load container ships, the lift stations that pump fresh water or wastewater. Right now, everything is really dependent on the grid, and what you can do with the microreactors or small modular reactors is have that behind the meter off-grid capability and really add a resiliency to your critical infrastructure by distributing and all these critical cannot failure type of points of vulnerability. You can mitigate the risk by having a distributed off-grid power supply at each critical node. On the commercial sector, there's just a plethora of applications. Think about remote villages or isolated island communities, villages in Alaska, Canada. We're really the right size to power about 30 to 50 homes. The current rates that they pay the islands, in fact, because they have to ship all the fuel out there, it's usually upwards of $1 a kilowatt hour. And again, since we're in that competitive range at less than 50 cents a kilowatt hour, we would be cost competitive with the current systems out there. And again, not need all that logistics infrastructure. Go plats, those gas and oil platforms, they could use the combined heat and power. Same thing for mining sites, remote mining sites. Talked about the data centers. Interesting thing about the electrification of vehicles with the Class 8, which is the large semi-truck class of electric vehicle. You really don't want those charging stations to be plugged into the local grids or the national grid, because they're really going to surge demand, different times of the day. So if you can imagine, a network of Exxon stations or Wawa markets that have their own microreactor to provide the power to refuel these electric vehicles. It's going to reduce demand on the grid and really balance out that electric infrastructure to keep those vehicles moving. SMRs and micros can be the load balancing for renewable energy. Solar and wind, like I said, they're not reliable 24/7 or 365. But if you have a reactor that kind of stabilizes that and becomes the load balancing solution, it increases the effectiveness of the overall energy generation capability. Industrial farms, we don't have International Harvester building EVs yet, but if you think of combines or big tractors that could become electrified, industrial farm could have a reactor there as its core for recharging those vehicles and then providing the heat and power for facilities as well. Luxury maritime, we've actually been approached by a European conglomerate that's building super yachts. They're interested in using reactors for power and propulsion of their high-end yachts. And some of these five-star resorts that are on remote islands that it's a little island of luxury on an island of a third world infrastructure. So, powering the hotel or the dock facilities at those resorts is a pretty compelling solution for them. And then even on the larger ships, the larger merchant marine ships like oil tankers and container ships, our reactor is not necessarily big enough to provide the propulsion, but we could be an auxiliary power unit like an APU to keep the ship warm while it's in port, continue to operate the cranes and all the life support functions on the ship so they don't have to run their big engines. And eventually those ships are going to be moving to the nuclear world as well. International Maritime Organization has a big decarbonization initiative to try and decarbonize the fleet by 2050. It's pretty ambitious, but nuclear powered commercial merchant ships are going to be on the horizon here shortly. Get into some of the challenges and risks. Obviously, the technical risk is there. We've got what I believe is a solid design, doing some independent confirmatory analysis with third-party integration challenges to bring all those pieces together. But I think the larger risks are things like the licensing and regulatory delays. The environment is getting more favorable. So I think there's going to be, I already sense a real willingness to work with the DOE and the national labs to move forward with the regulatory. Nuclear fuel is a big issue. TRISO is a great fuel, but it's going to be limited quantities and high demand until the supply chain starts manufacturing it. The public perception, that's turning a corner as well. There will still be not in my backyard, and we don't plan to transport our reactor by helicopter over any states or anything that's really a military application. But there's a strategic communications and messaging campaign and building confidence in the public as we continue to grow these capabilities. Then there's the customer demand itself. The Army, Navy, Air Force, Marines, they may change their priorities. Right now, there seems to be a pretty strong demand signal, but the developmental roadmap for these capabilities is, years. It's going to take 3 or 4 years before something is actually commercially available, if not longer. And those priorities and demand signals could change over that time. I think to address this, we have to be proactive. We have to be explain our innovative technology and do proof points as we advance the technology. We have to be transparent and collaborate, and then communicate. And then for you guys, specifically the same audience, the call to action, what I think you can do to participate and help advance this technology is to validate the requirements. Right now, there's requirements in the operational side of DoD to decarbonize and to really look at energy solutions, but they really haven't embraced mobile reactors specifically in the solution set. So it'd be great to get GONs or JUONs, some actual validated requirements. And then once that's done, the programs kind of come to life. The interdisciplinary input for system design, everybody from the logisticians to the supply officers, understanding the concepts of operation. How would these be transported? How would they be sited? How would they be employed in different operating areas, whether it's overseas or domestically? The lead for energy resiliency, critical infrastructure, the National Guard voicing support for these capabilities would be a boon. Advocating for favorable regulatory and policy oversight. I didn't mention it before, but the international policy is going to be just as important as the domestic. Especially if we're putting these on ships and moving into commercial ports and things. We're going to have international agreements to have the oversight and regulatory approvals to do that. And then just generally building awareness and educating the public. I think the safety record and track record is very strong with nuclear. It's a highly regulated industry that makes for sometimes slow movement, but it also has an evidential basis for backing claims of safety and backing claims of how reliable it is. I came primarily out of the aviation world and another highly regulated industry with a great safety track record. So a lot of parallels there. But if you don't build the awareness and educate the public on what those true risks are, then you won't move forward. So I think our company, as well as others in the industry, we're really looking to partner with stakeholders who envision an energy future that advances national security and addresses some of the global energy challenges that the whole world is facing right now. And I think with that, I'm about out of time. I want to leave some time for Q&A. I know I talk fast and I throw a lot of information, but I'd love to open the floor for questions and get your feedback. Thank you.
Well, hey, Chris, that was great. Really appreciate it. Well, we have a ton of questions, so thank you for that. So we'll why don't we dive right in to it? So if we kick it off, this is from Commander Amadasu. He says, can this be used to replace emergency power systems like on-site generators?
Absolutely. Yeah, that's probably one of the big takeaways is that, that's the target market we're looking for, emergency generators. But I would say generators that aren't just used in emergencies, but something that can run 24/7 and it's there when you need it, maybe to replace your prime power. But yes, emergencies. I think the mobile feature, it could be powering something on a day-to-day basis, and because it's mobile, you could pick it up and move it to a point of need. I think a good example, we've looked at some of the Hampton Roads infrastructure around Norfolk. There's a lot of critical federal installations there. There's Jefferson Lab, a lot of different critical infrastructure that's kind of a cannot fail type infrastructure. So you have things powered by the grid, and if they do fail, you provision for picking up a mobile reactor and plugging it into a local grid to continue the operations. So yes, absolutely, you can do that emergency backup generator.
Great. And so Jack asks, he said, excellent presentation, Chris. Have a few questions. You might be able to address this from the HALEU, HALEU, the HALO cost. Shielding, the original designs were something like 250 meter standoff in the role of Project Pele.
So HALEU, it really is you think of uranium, it's a mineral, but it's the isotope uranium-235 where the energy is. The military applications for carriers and submarines or the weaponized weapons, uranium is highly enriched, 95% or more is 235. The current reactors out there in the commercial world are low enriched uranium. That's 4%, 6% typically. What the HALEU is what they call high assay low enriched uranium. So it's still in the lower end of the enrichment, up to about 19.75 enrichment to be exact. And that gives you a higher energy density than what the current reactors use, but it's not something that's up at the high end with the weaponized or military applications. The supply chain is building out. There's Centrus, there's Orano, Framatome, the Nanonuclear all have ambitions to start producing these highly enriched the HALEU uranium fuels. But it's almost like a chicken and egg. The demand signal has to be there before companies will make big investment, and vendors won't sign up to buy their uranium until the supply chain's there. So I think it's going to take some government stimulus to build out that supply chain and before it kind of prime the pump to get it self-sustaining. I'm sorry, what was the other part of the question?
Hang on, let me get it. By the way, I'm just going to keep bombarding you with questions. I hope you're okay with that.
That's fine. Yeah, rapid fire.
All right. And how does this relate really in the role of Project Pele?
Oh, Project Pele. So That's actually a project that was awarded to BWXT. They've hosted us down at Lynchburg. I've seen the Project Pele prototype. It's on its way out to Idaho National Lab for testing there. So Project Pele was the DoD, actually Strategic Capabilities Office effort to build out a SMR modular reactor that could be demonstrated. It's bigger than ours, but our technology is very similar. So we've actually been called Son of Pele by Jeff Waxman, the Pele PM. So very similar technologies. Our feedback from people we've talked to in the military at pretty high levels is that there's kind of a wait and see attitude to see how Pele turns out before they move forward with any other kind of reactor design. That's hurt us a little bit, but there's plenty of private investment that can keep us going. But yeah, I think Pele is more of a fixed facility or something you transport every few months or few years. It can go forward just like a microreactor, but it's not going to be something that moves forward during an operational campaign. It's really something to do more of a facility or installation type of a power. Our reactor I envision being coupled with things like the counter UAS systems, those directed energy systems to do base defense at a FOB. Pele is really going to be more of a bigger reactor to actually power the FOB itself.
Got it. Okay. These next few from Charles, I'm going to kind of wrap them into kind of one overall, two questions. But so are there any, you mentioned that there are civil customers, the type of civilian customers that can buy this, but are there what are the regulatory requirements, and what are some of the maintenance requirements on this? And do you have to have any type of training or certifications for this as well?
Another great question. I think a lot of the regulatory challenges that we're moving into uncharted territory. We haven't had mobile reactors in the commercial sector, especially in the past. So we're going to have to work closely with DOE and other regulatory bodies to make sure we have the right protocols and safety in place. A good example, I know I came out of General Atomics, a big drone manufacturer. We had ITAR oversight. We had Missile Technology Control Regimen. You're going to find the same thing in the nuclear world. Bodies like the International Maritime Organization. We're actually talking to the American Bureau of Shipping, how to establish training programs and certification programs. For aviation, you have things like A&P mechanics, aviation, power plant mechanics, things, guys that actually have a certificate. So you'll have the academic accredited institutions that can actually award degrees, but then you're going to have more of a vocational track as well for those licensed operators to service, maintain, and operate the reactor systems. So yeah, it's a consideration, but again, uncharted territory, and with the right congressional support and relationships we hope to establish throughout the community, I think we can all move forward in that regard.
Okay, great. And then could you ballpark what the initial cost would be for, say, 1 megawatt?
I'm sorry, one megawatt?
Yes.
Well, our reactor design, the nth of a kind, which means once you enter your full rate production,
Yeah.
A fully filled reactor, we're probably in the ballpark of $13 to $15 million per unit.
Okay.
Assumptions there, but the math.
Yeah, no, that's why I said ballpark. Yeah. That was good. Just another.
And that gives you a reactor that has the 10 years of fuel, and that's how we get that 40 cent per kilowatt hour number.
And then Rob Burton asked, looking at the type of output, is it 480 volts, 3-phase, 60 hertz? What kind of output are you?
Our vendor we're teamed with to build that supercritical CO2 turbine generator, it's rated at about 350 kilowatts. I believe it is a 3-phase. I'd have to get back. If he wants to send an email or follow up, I can provide more information on that. But I do know it's been told to me it's conditioned clean power. So it's whatever that generator rating is, I'd have to look that up and
okay
on that.
And
also has black start capability too, so it can start without priming.
Absolutely. And so how does operating a mobile unit fit with states that have restrictions or permits for new reactors?
Well, the DOE has the site-specific licenses where you do the environmental impact studies, and you actually get approval for a specific site. There's also something relatively new called the design specific license, where they certify the reactor design itself. It's still going to require some siting requirements and approvals for placing it, but it's not as extensive as building another 3 Mile Island or Clinch River or something like that. So again, this is something we're going to have to work through with the right bodies. This is kind of a lockstep effort of maturing the technology, advancing the policy, and building the public acceptance. I think we've got a good vector going forward, but a lot of those questions have not been fully answered yet.
Okay. Paul asks, is there any infrastructure in place for the reprocessing of the fuel?
Yes, actually, our fuel could be burned in a larger reactor. So we've talked to Oak Ridge National Lab about the full fuel life cycle. Nuclear fuel cycle is a critical consideration. It has to be designed in from the early get-go and design of the reactor. But when nuclear fuel is quote unquote spent, there's still a lot of energy in that fuel, and we could take that and burn it in a traditional larger reactor. So we don't see ourselves, creating big stockpiles of fuel waste. And we intend it to be a closed fuel cycle where it's reprocessed or burned by another system.
Okay. And have you modeled, who is this? I apologize. From John asks, have you modeled environmental cleanup should there be an accident?
We have not rigorously, just at a pretty high level. I think the worst case would be a kinetic strike on the reactor itself. What happens when there's a direct strike on the 20-foot shipping container? Because the helium gas doesn't activate, and because we're not producing anything that's going to seep into the ground, you're not going to have any aerosolized radioactive going into the atmosphere. You're also not going to get any groundwater, seepage into the ground. You're basically going to have a localized cleanup site. The clad pellets themselves will probably not break open because of the explosion. They'll probably stay, those little poppy seed size or annular sized pellets should stay physically intact. So you're going to have a site, depending on the debris field, that you could go over with something like a Geiger counter and just scrape off that top. The military and even the civilian community deals with a lot of environmental hazards, everything from hydrazine to diesel spills, whatever it might be. So we don't take that lightly at all. It will be a non-trivial task, but we don't think it's catastrophic. We think any kind of even a gross physical destruction of the unit itself could be managed and cleaned up. We're also the shield modeling we have. We're not going to activate the ground, so when we pick up and move, there's not going to be residual radiation. Leave behind. Kind of like the Boy Scout motto is "Leave no trace."
Great. Yeah, and that leads into the kind of the next question. You gave us an overview of how the reactors put together, but what type of materials are you using to shield the radiation?
Some of that is proprietary. So think of bismuth or lead. Weight is definitely a consideration for us because we're mobile. But we're looking at some different options, things that will maintain the shielding properties even if they've reached their melting point. For some of the maritime applications, we have options to do a water jacket, surround it with water. We're also considering things like starshine. If we're doing a helicopter transport, we don't want any radiation going up, even when the reactor shut down. So the shielding has to be 360 degree all the way around. We have some preliminary models that say we can stay within our size and weight parameters that we're targeting. But as we move forward with the development, we're going to have to do more high fidelity modeling and simulation to validate that before we actually start building out the physical prototype. But those are the kinds of things that we're really partnered closely with the national labs, Idaho National Labs test facility. They've got all the instrumentation to validate the assumptions. Same thing with Oak Ridge. So, that's a high priority for us, is that shielding and safety.
Absolutely. We have a couple more questions. Hopefully I haven't burnt you out too much on the question, but it definitely seemed like there's a lot of interest around that. I do have a couple of SME slides, but if anybody wants to stay around and ask Chris any additional questions, he does have a few minutes after this. I just need to wrap up, so we're done by 1 o'clock. But no, this has definitely been a very, very engaging and we do need to take a pause for questions, and we can get right back to it in a moment. But thank you, everybody, for participating in today's session. We do appreciate your time here with us today. But before we wrap up our program, I'd like to share with you some upcoming events that we do have planned. So please mark your calendar.
Before you jump into that, Whitney,
Sure.
if I could just say, I really appreciate everybody's time and attention as well.
Absolutely.
If you have any questions or follow up, don't hesitate to reach out to me directly. So I appreciate it. Thank you.
Absolutely. Yes. So please mark your calendar for some upcoming local post events and national SAME national events. Our next First Friday webinar is professional ethics for architects and engineers. So doing the right thing, even when no one is watching, which will be presented by Doug Hipschman and Dana Molinari from Fox Rothschild. We will be learning about the ethical requirements for architects and engineers and offering practical guidance on applying these principles in real world scenarios. And it is open today if you'd like to sign up. Are you interested in sharing your knowledge on current educational topics on the First Friday series with our members? We are now accepting presentation abstracts for 2025. Please visit our website to learn more and submit your topic today. Sponsorships are also available to help support our popular program. Several national programs are in full swing. We'd like to invite you to participate. We're getting ready for the premier training conference of the year, the SAME JETC, which will be held May 13th through 15th in Louisville, Kentucky. If you're interested in nominating an individual or project for an award, the deadline is Monday, February 3rd. Learn more at samejetc.org, and registration opens at the end of this month. SAME is back with their 2025 Career Transition Workshop. This is a two-part event. The first is the virtual training, which will be held online on January 14th. The second is a live in-person program, February 12th through 14th in Lyceum Heights, Maryland. If you're interested in learning about the transition from a career in the military to private industry, we're looking to firm up to recruit transitioning veterans, please join us for the Career Transition Workshop. And don't forget about the 2025 SAME Capital Week. The members only and bring access to leadership from across federal agencies to share an outlook on procurement budgets and planning for 2025, right in our backyard in North Bethesda, Maryland. And we do also have a busy DC Post schedule. Join the DC and Nova Post for a fun tour of the DC Blue Plains Water Treatment Plant on Wednesday, January 22nd. This event is filling up quickly, so don't wait and get your tickets today. And join us for the 29th Annual DC Post and Military Branch Service Awards that will be held at the National Press Club on Wednesday, January 29th. You won't want to miss out on our signature awards event that celebrates the successes and achievements of individuals and firms throughout the AEC industry. Sponsorships are also available. So please reach out to me if you have any questions. The event sold over 200, there were more than 200 attendees last year. So we are adding seats to accommodate even more. So don't wait, and please register as soon as possible for this popular program. And on Tuesday, February 25th, we're supporting our military and families at a fun NHL night at Capital One Arena for the 23rd annual salute to the Military Appreciation Game. The DC Post has a section reserved for our members and guests to enjoy the night at the arena. Net proceeds for our ticket sales will go to the veteran program, River Runner. Tickets are going fast, so don't wait to sign up. And we'll have more events planned throughout the rest of the year, so please be sure to visit our website to see the full list of our educational and social events throughout the year. Connect on LinkedIn, that we share news, photos, and building a strong network throughout the AEC industry. We can't wait to watch all the past First Friday webinars as well. And would you like to reach a community of 7,000 architecture, engineering, construction, technology leaders? With the SAME DC Post annual sponsorship, you have the opportunity to leverage our network to showcase your firms with visibility and international recognition you won't get anywhere else. So support us with an annual sponsorship like this First Friday series and individual events throughout the year, like our upcoming awards program at the Press Club. Check out all the benefits and support this popular and support the mission of DC Post and your community today. So thank you all again for attending the first Friday webinar with Chris and providing the educational content today for our January 1st Friday webinar. Chris will stay on for a few minutes if you have any additional questions, but also look out for a document delivery subject line with a slide, PDH certificate, opt-in list of registered participants today, and we'll be posting the recording on the DC Post website later on this month. You also get an email from our presenter with more information and what was presented and how you can sign up for their newsletter and announcements as well. And don't forget to download the chat before you leave the webinar. Again, thank you to our DC Post First Friday sponsors, Fox Rothschild, KCCT, and Parsons. So on behalf of myself, Bree Beal, and Samantha Long, have a great weekend. We look forward to seeing you at the SAME event soon. So thank you. So I think we had one or two questions, Chris.
Yeah, just looking through the chat here.
Yeah, I think, let's see, Charles.
Repowering the Savannah. Yeah, that's a great question. I actually used that example in a presentation I made to the U.S. Coast Guard and Navy recently. So that was part of Eisenhower's Atoms for Peace program. I don't know that we would repower that, but you know, other ships that might be in the ready reserve today would definitely be willing to try and power those. I'm not sure what the Savannah is. It's probably a museum. I think it's in the Baltimore Harbor now, but I think the cost to refurbish that would be pretty high. And it really wasn't the most efficient cargo ship. It was more of a you know, show the flag and demonstrate the capability, but it really didn't contain the amount of cargo to make it economical. The question though about using our power to provide that backup power for the larger ships, yeah, I really think that's a great application, that auxiliary power unit, whether it's a ship that needs auxiliary power when they're in port, or a backup power for you know, other systems, critical infrastructure. You know, this is the right size to provide that cannot fail kind of capability, or even like a data center. The data centers typically require megawatts of power, but there may be some critical pieces that would, you know, be the perfect size for our reactor to keep them up running. So they fail gracefully, basically.
Okay, Bradley, Brad Flott asked, so is there a small unit plan to providing 50 to 100 kWs for localized compounds or building use? So I think that's what you were addressing.
Yeah, and we are looking at a technology. It's not as far along as our current reactor, but there's a 40 kilowatt scale reactor that is a smaller one that we want to add to our portfolio, and that would be really sized for that smaller application like that.
Okay. Let's see, Bill Beal. Hey, Bill, has there been any consideration for using mobile microreactors in place of diesel generators for emergency backup power to mitigate the risk of a station blackout at traditional full-size reactors?
We've considered that as a possibility, but we haven't had direct talks with any of the reactor vendors about that yet. But yeah, it's that fail-safe power that's really the target market. One of the target markets we're pursuing. It's a great application. Great question.
Okay. All right. Hang on. I'm going through here. Let's see. Hang on. Let's see. Let's see. Going to ask about cleanup. Let's see. Hang on a second. I think there was one more question we had on here for you. Was
saving the chat while you're finding that?
Yeah, go ahead and save the chat if everyone hadn't saved the chat. I think that was yeah, okay. I think that was, unless I missed it and I apologize, because I'm glad there was a ton of questions. That's what we wanted to get to in the presentation, but this was the chance to get the engagement going with you. So I think that was That was great. I think the only other one I saw was are there any regulatory limitations with utilizing these nuclear systems in the U.S.? But you addressed that on how you have to work closely with them right now.
Yeah.
So.
Yeah.
Okay. All right. Well, that's all I have. And again, I apologize if I missed your question. If so, Chris has his contact information in the chat. Make sure you save the chat before you leave, and feel free to reach out to Chris directly. And with that, we'll close out. So thank you, everyone. Chris, thanks a lot for your time, and we look forward to seeing you out at the next event.
The award ceremony.
Yep. Okay. Great. We'll see you at the
there.
award ceremony.
Yep. Okay. Thanks, Whitney. Thank you, everyone.
All right, thank you.
For your attention again. Bye.
Yep. Bye.